Dear colleagues, welcome to the last part of our conference, and we started with a talk by Spanish astronomer Dr. José Caballero, who will guide us through stellar variability from high mass, high luminous stars to low luminous brown dwarfs. So, José, it's yours.
Hola, dobrý den.
Dobrý den.
Just if you don't understand me, just interrupt me at any time, or if I'm close to the end of the time, just tell me, Jose, hurry up. Let's start. I repeat the title, Substellar Variability from 20 solar masses to 13 Jupiter masses. And as you can see to the bottom right, I'm calling you from Spain. First of all, I want to thank Marek because of contacting me and preparing the logistics of all this, and also to Jakub Judicek. Jakub was in a meeting in September 2015, also in Spain. It was an international professional amateur meeting binary multiple star systems, and there I gave a talk. The talk had a similar title, binary systems from 0.2 arc seconds to 2 degrees. It is not the same giving a talk just being there or making it by Skype like now, but the thing is that Jakub liked the talk and then proposed me to give this talk in your meeting, and I will use exactly the same structure of that meeting, which was just showing what I have done in my 16 years of career. Let's break the ice. You are in Ostrava. For me, it's a place far away, because if I wanted to take the car, then I would need about 24 hours without stops to reach there. Last week I was in Munich. On Wednesday I have to be here, so that is the reason I am not now with you. Okay, you are in Ostrava and I am in El Escorial. This is where I am right now. This is my hometown and where I live. Okay, let's go to science. This is your website, Czech Astronomical Society, or better, České astronomické společnosti. Sorry for the pronunciation. And this is the program of today, and with the 20 minutes delay, we are in the previous to the last talk. Afterwards, there will be another one by Reinhold Auer. And let's start. And as I told you before, I will use the same structure as I did on my talk on professional amateur meeting and binarities. First, variable star. All of you and all of us have been told that it was Mira, Omicron Keti. It was first discovered in 1596 by David Fabricius, but he thought that it may be a nova. Johannes Holbarda was the first one to measure the periodicity around 11 months. Another Johannes, in this case Hevelius, wrote a paper and give the star the current name, Historiola Mirae Stellae, and that is the reason I said Mira, not Myra, as the Americans said, because if it is Latin, it should be Mira. And in 1667, Ismail Bouler made the calculus of the period, and it was 333 days, which looks like a lot to the 332 days that we know today. It has been suggested by some authors that even the Babylonians, the Chinese, the Korean, or the Greek knew that it was variable, but it has not been confirmed. Okay, so Mira, it is what we have been told. But remember that 24 years before, Tycho found or gave the name to his supernova, the supernova 1572. Kepler a few years afterwards. But 500 years before, there was the Chinese supernova, supernova 1054. I suppose that you understand, like me, that the supernovas are also variable stars. It was not only the one of the Chinese, which was also observed by the Arabians, and what we called before Anasazi. Half a century before, there was this supernova of 1006, seen by the Chinese in the dynasty Shang. But it was in one of the books of an Egyptian astrologist called Ali ibn Radwan. It was observed by the monks of the Abbey of St. Gall in Switzerland, and even it was observed from Yemen. And even that, we have the supernova of 185, also observed by the Chinese and perhaps by the Romans. But what was the first variable star really? Not Mira, not the supernovas. The real one is Algol, Beta Persei. We've been told that it was the first variable after Mira. It was discovered by Gemini Montanari in 1669, but actually it was discovered by the ancient Egyptian scribes and tabulated it in the Cairo calendar in the 12th century before Christ. And actually they could measure the periodicity of 2.85 days, which looks like a lot to the periodicity that we have, that we know right now, of the order of 2.87 days. In any case, there was some suspicion of this variability because the Arabic gave it the name Ras al-Ghul, which was a Mesopotamian demon. And even the Indians used the word Majavati, which means the changeful, for Algol. So this was if you are ever asked which was the first variable star, just answer Algol. Let's go with the other piece of history, but in this case, my history. I read my thesis in 2006, and the title of the thesis was Formation, Evolution and Multiplicity of Brown Dwarfs and Giant Exoplanets. And there you have a table that tells you the differences between stars, brown dwarfs, and, let's say, planets. Not regardless where they were formed by, but on the physics of the interior, which means that the stars have burning of hydrogen and of deuterium, and thus they have a mass of around 0.075 Jupiter solar masses. A brown dwarf burns deuterium but does not burn hydrogen, and a planet does not burn anything. The boundary between stars and brown dwarfs is at around 72 Jupiter masses, and between a brown dwarf and a planet at around 13 or 14 Jupiter masses. For characterizing spectroscopically brown dwarfs, planets, and very low mass stars, we need to extend the classical series of spectral types. Oh, be a fine girl, kiss my lips tonight, yeah. With the new spectral types L, T, and Y, which display some features, for example, of absorption by dust, by water vapor, or by ammonia in the case of white dwarfs. At the beginning of my thesis, the first thing that we wanted to do was searching for transits of planetary Earth-like planets around L-dwarfs, around brown dwarfs. And then we studied which was the habitability of having habitability of these planets around brown dwarfs, and how they could be detected by transit. And we made an initial project of looking for eclipses of transits of L-dwarfs. It was the first near-infrared photometric variability survey of L-dwarfs all over the world. It was performed in J, H, and K short bands with a 1-meter telescope in the Canary Islands. Just to let you know the real fineness of these objects, the one in the center is Kilo 1, Kilo 1, and the magnitude in J is 1341, in I is almost 17, which means that in V is of the order of 20 magnitudes. So we are talking of really very faint targets. What I was able was to measure the stability of this brown dwarf with an accuracy of 8 millimagnitudes, 0.008 magnitudes. There were no transits. We studied more. This was the first publication in a conference on the investigation of variability of L-dwarfs in the near-infrared. It was in a conference in Hawaii, which was held in 2002. We continued our project, and eventually we could not find any transit, but what we could see is the intrinsic photometric variability of the atmospheres of the L-dwarfs, especially of the late L-dwarfs, close to the transition between L-dwarfs and T-dwarfs. That transition occurs at at effective temperatures of the order of 1300 kelvins. Remember that the effective temperature of the Sun is 57,500 kelvins. So we are talking of objects that look like more planets than stars. Well, we eventually published within a large international collaboration called CLOUDS, Continuous Longitude Observations of Ultracool Dwarfs. We published our preliminary results on this, and we coordinated our spectrophotometric observations with telescopes in India, France, the Canary Islands, North America, and Hawaii. But the main issue was that the variability that we were detecting was not convincing. Fortunately, some friends of mine in Montreal, in Quebec, Canada, they found the real, completely sure variability in L-dwarfs. They were Etienne Artigot in 2009, and especially Jacqueline Radigan in 2012. Artigot at the top, Radigan at the bottom. They discovered very clear photometric variability in early T-dwarfs with effective temperatures of the order of 1000 kelvins and periods between 2 and 8 hours observed in both in J, H, and K bands. Since it seemed that with the 1.5-meter telescope in the Canary Islands, which was very old, I could not investigate well the photometric variability of brown dwarfs in the field, then we decided to go to a young region, which is more distant but much younger. Distance is around 385 parsecs, and the age is 3 megayears. just for comparison, in the field what you get is ages of the order of giga-year and distances of the order of 10 to 20 parsecs. This young region is the Sigma Orionis, and Sigma Orionis is this star. You may recognize Al-Nilam and Mintaka, which is the Orion belt, and here you can see the Horsehead Nebula. So Sigma Orionis is the star which illuminates the Horsehead Nebula, and is very famous because of the studies in X-ray emission, high-peak objects, stars and brown dwarfs with disks, and something that we call the initial mass function, which is the Sigma Orionis is the place where it has been investigated in better detail. To sum up, Sigma Orionis is the place where you can find more brown dwarfs. It's full of brown dwarfs. Sigma Orionis is also the name of the star, and when the name of the star that gives the name to the cluster. And somebody can think, oh, maybe we can investigate the photometric variability of Sigma Orionis, the A and B stars. Well, actually, you have 3 stars in the system, plus B, plus C, plus E, plus several others. So in the end, you have a 16-tuple system, 16 stars there, and of them, only one is reported to be variable, which is Sigma Orionis E, with a period of 3 days, but it is something of the order of 20 masses, the first 20 solar masses, the most massive one, 8 solar masses, the one of Sigma Orionis E. But what if we go to the other side of the mass? 25 Jupiter masses. 25 Jupiter masses was the mass, or is the mass of S Ori 45. S Ori 45 is a brown dwarf Sigma Orionis cluster, spectral type M8.5. With 3 megayears old, it corresponds to such a very low mass. And in 2003, in the meantime, I was looking for the transits of field L dwarfs. We took some observations in the near infrared of SORI 45, and we detected a tentative period of around 3 hours, which could be related to heterogeneities, spots on the surface of this young brown dwarf. That was only one, and that you cannot do any statistics with it. When we want to observe to study the initial mass function of the cluster, we need to obtain very deep images. For obtaining very deep images, what you have to do is taking a lot of long images. For example, 100 images of 15 minutes. Observing the same field for 4 nights consecutively. Then you have a series of images on which you can do photometric variability, and you can look for photometric variability of brown dwarfs in the cluster. That's what we do, or we did in 2004 with the 2.5 meter telescope of the Canary Islands, Isaac Newton telescope, and the Warfield camera, the instrument, and half of the brown dwarfs and very low mass stars that we investigated showed some kind of variability, and the amplitude of variability ranged between 0.01 and 0.4 magnitudes. Something that we discovered was actually expected, because it is something related to the T-Tauri phase of low mass stars, is that the most active is a star, or the largest the flux excess because of the presence of the disk, the larger the amplitude of the variability. The most variable brown dwarf that we detected in our survey, we did not have a spectroscopy for it, but it had a clear signpost of having a disk. This work was the origin of some theoretical investigations on pulsations induced by deuterium burning by some French and Italian college, and it was mentioned in the yearly review by Virginia Trimble in 2006. The most variable brown dwarf in the survey before was the subject of a most dedicated work using Keck, the Nordic Optical Telescope, and two relatively small optical telescopes for photometric monitoring. We use an 80 centimeter telescope and a 1 meter telescope to investigate the photometric variability of this brown dwarf in Sigma Orionis of a very long name that now has received a variable Orion 9 of variability. Then what we found is that it was indeed very active with a strong H-alpha emission, and that it showed amplitude of variability of up to 0.7 magnitudes, which makes almost 10 years later to be the most variable brown dwarf ever found. Okay, that is a success, but maybe there are more. Since we knew that the most active mean the most variable, we did the reverse search. We was looking for the most active ones and then try to look for the most variable, and that is something that we did in this work. And what you can see in this plot is that the circles mean amplitude of photometric variability. The most variable tend to be in the top part of the diagram, which are also the most active ones. And there are few variable stars and brown dwarfs in the lower part, which means low active. I will be back one. This star here is relatively bright and relatively active for its expected mass, and is the spectrum of this one on the top of this image. The other are other spectra. The name of this star is Merit 459-350, originally known as STHA50. It is an early A star with emission lines. This is H-alpha emission. H-alpha of -10 in an early A dwarf is a lot, is huge emission. And we are talking of about 1.4 solar masses. Besides, it has mid-infrared excess, which means that it has a disk. And the funny thing of this star is it has very abnormal colors, a lot. I mean, that when the spectroscopy is clearly of a A dwarf, the photometry tells you that it is a B dwarf, but depending on when you observe it, because sometimes it looks like a K dwarf. So, what I do now is making homework for the České astronomické společnosti. Homework 1 is quantify long-term high amplitude variability of Merit 459-340. It is achievable with your telescopes because magnitude is 11.3, and the aim is confirming the scenario of UX-ORI type of variability, which is a bluing effect in heavy AEB stars. Heavy AEB stars are very young stars just formed that have a scattering edge on disk, which makes this bluing effect. We have no photometric variability monitoring of this star, but from the spectra that we have seen a brightening of almost 1 magnitude in only 1 year. I think that this is a straightforward measure with small telescopes now. I thought that, okay, if this is one peculiar variable, there might be most. So a couple of years ago, we did a professional amateur collaboration with Ramon Naves, who has 30 centimeter telescope, semi-automatic, and with a student of mine, of master thesis, and then we monitored as an area of Sigma Orionis, of the Sigma Orionis cluster during one winter, and apart from discovering or rediscovering a lot of variables, I noticed one that it was very strange, very weird for me, is this light curve. It corresponds to an A0 star, and we can see a period of around 1.6 hours and an amplitude of only 17 magnitudes. Homework 2 is better constraining the period and the amplitude of photometric variability of this star, made it 55460, which has a Henry Draper name. So that means that it is very bright, it's 8.5 magnitudes. Why it is important, this star? Because it's with this period and this spectral type, it could correspond to a delta Scuti star. But there are no delta Scuti stars as young as 3 megayears as this one. So it can be a cornerstone for the study of the interior of very young stars of around 1.5 solar masses. There are more amateur astronomers interested in this project, and maybe it is better to do it from Italy, because what we need is something like 3 hours per night during a few nights, get an accurate light curve of the star. But of course, if from Czech Republic you can see this star for a long time, above Air Mass 2, then you can do it. Of course, one can go to public databases, as this one, using the ASAS, or the Sky Automated Survey, ASAS, made by the Hungarians, and can look for the most variable stars in the Orion belt. And you can see again Al-Nitak, Al-Nilam, and Mintaka. Okay, so I did it again, and I found 32 highly variable stars. And when I say highly variable, it means more than 1 magnitude of peak-to-peak variability. Of them, 16 were new young stars of type Herbig or Titauri, 8 were giants, and the other 8 were miscellanea, including cataclysmic, eclipsing, and some contact binaries. Of them, 16 were new, half of them. And this is, for example, the face-folded light curve of one of the new giants with a periodicity of around 300 days. And the amplitude of variability is of the order of 1 magnitude, 1.0 magnitude. Homework 3 is improving light curves of the 16 new Orion belt variable stars. These probably are a bit fainter, with magnitudes between 11.5 and 15, and it includes 6 giants, 6 eclipsing and polygon variables, and 4 young stars, which names I give there below. Of course, you can go to the original publication. Why for me investigating the young stars is interesting? Because you can be lucky and find something like this. This is the light curve of V1247, and it published in a letter in Astronomy and Astrophysics. Okay, so what you can see there is a standard early type star, relatively flat in Larcos, but with occultation events. I investigated the star in detail, and what I found is that it has near-infrared and mid-infrared flux excess, which means that it has a disk. Actually, it does not only have a disk, but by several of them. It has one outer cold disk and another one warmer and closer to the star. And besides, there might be some gas in the interior. I explained it, the occultation of events of this star by clamps heterogeneities in the inner wall of the warmer disk. For that, I was very happy when I saw that a group of international astronomers took a spectroscopy with the space mission Spitzer, took photometry with WISE, used the VLTI, the interferometer of the VLT, and made a detailed analysis of the star and confirmed my hypothesis of the star in the center having an inner disk and outer disk with some rarefied gas in the middle, and then what it makes the occultation is some clamps heterogeneities of an almost edge-on disk surrounding the star.
Jose,
Yes?
I'm very sorry for interrupting you, but you're already out of time, so please could you go faster, just to have a few minutes
Okay,
for some discussion.
this is the last one, or the previous to the last one. I can do also photometric variability but in X-rays, and the really last thing, it was Carmenes, what is a machine for discovering exoplanets around dwarfs, and you will have the presentation available in the website, and this is the homework number 4, which is confirming the photometric periods of 3 dwarfs that can have transits by planets. So, summary and conclusion, your team can do a lot of usable things between professional and amateurs. And that's all. Děkuji vám. Thanks. Gracias.
Thank you very much for very interesting talk. And now we have space for a few questions. So, do any of you have a question? No question? Okay, I'd like to ask you what kind of photometry you are interested in our homeworks. Should it be a color photometry, and in what filters and?
For example, one collaboration that I can go fast to this in the meantime. One collaboration that I did with amateurs already, the one with the 30 centimeter telescope, this one, it was done with white light, and we realized after taking all the data that we had some color effects. So the narrower the filter, the better. I would use some broadband filter. In the case of early type stars, B or V, and if you are going to redder objects, maybe R, which can be maybe the reddest filter that you can use with the CCDs available to amateurs. So it would be using some filters, going to the limit of the instrumentation to get the better photometric accuracy, and you are completely free to publish those data by yourself. Just tell me when they are published. You just send me an email. Hey, Jose, we have made this publication on this star, and we have confirmed your period, but it is not 1.6 but 1.7.
Okay, but I think that if somebody will measure these stars, so we will contact you before publishing, just to cooperate with you, because it's your project. So don't worry that we will publish something by ourselves and only then let you know. So okay, so color photometry is welcome. Any question? Nobody? Okay.
It was very clear.
Yeah, probably. I have another one question, if I could ask you. You mentioned some types of variability. You spoke about some pulsations due to deuterium fusion, and you spoke about rotation due to some spots. And are there any other effects which can cause variability? I mean, convection or something like these mechanisms.
Yeah, convection is more apparent in giants. In dwarfs, which are these kind of objects, we do not see the convection at all. Depending on the age, we will see more the spots or the activity, or just the weather, the heterogeneities in the surface. The thing of the pulsations are still science fiction, but we will need maybe a 10-meter telescope and being observing the target for a long series before confirming this thing of the deuterium burning. The problem is that this deuterium burning occurs during the first 10 million years of the objects. And this is when the objects are more active, and it is more probable that they have spots on their surface. So eventually what we will see is the rotation of the stars and of the brown dwarfs.
Okay, thank you. And you also showed one star with 0.7 magnitude change. What was the cause of this event?
In this case, is rotation plus disk. It has this strong H alpha emission indicates that the central high mass brown dwarf is accreting material from the disk. What we explain, the way in which we explain the variability was that what we see is not only the rotation and the spots on the surface, but also infalling material to the surface of the star. When the material is, of the brown dwarf, when the material is falling down on the surface, it is heated and it shows bright spots, not only dark spots but bright spots. And what we see is changing dark and bright spots during the rotation of the brown dwarf. Very complicated system.
Yeah. Okay, thank you. And last attempt to ask participants about some questions, or okay, it seems that nobody wants to ask you.
No problem.
Question. Okay, so thank you very much for interesting talk and for our homeworks. I think that at least few observers will try to measure your objects, because I saw at least 2 of them making some notes. So we will see if anybody of us will observe. So thank you very much. Thank you very much again. Bye.
Okay. Ciao.
Ciao.
Adios.
Ciao.